For topic two, we're going to discuss something called coterminal angles. So here's a definition. Two angles in standard position are said to be coterminal if they have the same terminal side. So we've drawn a picture here, and I'm going to kind of use different colors so you can see it better. We haven't drawn a picture here. We hijacked a picture, but anyway. So the first angle, if you're in standard position, remember your vertex is at the origin and the initial side of the angle is on the positive x-axis. So our first angle is open in the counterclockwise direction. This is angle A. It's positive. Now, our second angle opening in the clockwise direction is B. Okay? They both have the same terminal side, so A and B are coterminal. Now, the other picture we have, let's go back to blue. We have this angle right here in blue. So that's angle A, some positive angle. And then let's look at angle B. So angle B, it sweeps around and it does a full revolution and then it keeps going and does even more. And it ends on the same terminal side as A. So angles A and B are coterminal. They share a terminal side. Okay, so that's the definition of coterminal angles. It's really just any two angles that share a terminal side. But there's a little bit more to it, okay? Because coterminal angles share the same terminal side, the values, I should say then, the values of the trigonometric functions for coterminal angles are equal. Let me move coterminal. I'm not going to have enough room for it. So the trigonometric functions of coterminal angles are equal. So in this picture right here, the first image, if we were looking at the six trigonometric functions for angle A and comparing them to the six trigonometric functions for angle B, they would be exactly the same because they share the same terminal side. Same thing for the second image. We have two positive angles, but one does only part of a revolution, the other one does like a whole revolution plus some. Okay? A and B, if we were to look at the six trigonometric functions, they would be exactly the same for angle A and B because they share the same terminal side. Okay? And we already know that with any angle, if we have some angle, okay, in standard position, and if we know some point on the terminal side, then we have ratios for all six trig functions. For example, we know that sine is equal, this is r, we know that sine is equal to b over r, cosine is equal to a over r, tangent is equal to a or b over a, cosecant is equal to r over b, secant is equal to b or r over a, and finally cotangent is equal to a over b. We know that from the definition from our first video for this section. So if you share the same terminal side, you're going to have the same point on the same terminal side, meaning all of these ratios are going to be the same. And we use this to our advantage. Okay, so let's go ahead and look at example 4. Okay, let me actually shrink this a little bit so I have a tiny bit more room vertically. Okay, so example 4 says, use coterminal angles to find the exact value of the following. So for part A, we have sine of 13 pi over 6. Well, we know our denominator is 6, so let's break this Cartesian plane into sixths. So we would have 1/6 about here, 2/6, 3/6, 4/6, 5/6, 6/6, 7/6, 8/6, 9/6, 10/6, 11/6, and 12/6. Okay, so we have broken this thing into basically six. So we're looking at 13 pi over 6. So from 0 to pi, break it into 6 pieces, and then from pi to pi over 2, or from pi to 2 pi rather, break it into 6 pieces. So let's count out sixths here. Well, if we're going to have an angle, we have our vertex at the origin. We have our initial side on the positive x-axis. We go 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6, 7, 8, 9, 10, 11, 12, 13. So this is our angle right here. This is theta. We know theta is 13 pi over 6. Well, we did one full revolution plus a little bit more. So let's think of another angle that's maybe easier to work with that has the same terminal side as 13 pi over 6. Well, if I look right here at this angle, okay, let's say we call it alpha. What is that angle? Now, if it shares the same terminal side as 13 pi over 6, then all of the trig functions are going to be the same. So what is this angle alpha? Well, let's think about it. How far past the x-axis did we end up going? So we went more than one full revolution. So 13 pi over 6 is more than one revolution. Well, let's see what's left over, okay? So let's play around. So we have 13 pi over 6. We did one full revolution, and we want to see how much more than one full revolution we completed. So we know that one full revolution in radians is 2 pi. Well, I need to rewrite 2 pi with a denominator of 6. So let's think of this as 2 pi over 1. Well, the LCD here would be 6. So what would I multiply top and bottom here so that the denominator is 6? Well, I would have to multiply my denominator by 6 and my numerator by 6. So basic fractions, you need to be comfortable with those. So if we have 13 pi over 6 and we subtract 2 pi, that's really 12 pi over 6, meaning we did one full revolution and then we did pi over 6 more than that. So what this really means, since coterminal angles share the same terminal side, the trig functions are going to be the same. So sine of 13 pi over 6 is equal to sine of pi over 6. And pi over 6 is one of those super common angles that we need to remember. Remember, pi over 6 is really the same thing as 30 degrees. And we should remember that sine of 30 degrees is something. So if you go back to your notes for section 7.3, you have a table where we filled in the 6 trig functions for 30 degrees, 45 degrees, and 60 degrees, okay? And it just so happens that when you have sine of 30 degrees, it equals, or pi over 6, it equals 1/2. So that tells me this up here is equal to 1/2. So that's kind of this really cool thing. So sometimes if we have an angle that's kind of wacky, if we can find a coterminal angle that we're more familiar with or that's easier to work with, we know that coterminal angles are going to be the same for all the trig functions. So we can use that to our advantage. Okay, now let's do the same thing for this next example. So we have secant of negative 7 pi over 4. So from 0 to pi, let's split it into 4 pieces, and then from pi to 2 pi, let's split that into 4 pieces. So this would be 1, 2, 3, 4, and then we've got 1, 2, 3, 4. So we split 0 to pi into 4 pieces and then pi to 2 pi into 4 pieces. And let's just count off and see what this angle looks like. Okay, so we do have a negative angle here, so that means we are going to be opening. We're going to sweep open in the clockwise direction. So let's put our vertex at the terminal side, or at the terminal side, bless my heart. Let's put our vertex at the origin, okay? We're going to put our initial side at the positive x-axis, and then we're going to sweep open 7 pi over 4, okay, or 7/4 pi. So we've got 1/4, 2/4, 3/4, 4/4, 5, 6, 7/4, okay? So that tells me this angle right here, theta, is negative 7 pi over 4. But we didn't quite do a full revolution. So what would we still need to do to get a full revolution? Because 7 pi over 4 maybe, or negative 7 pi over 4 is maybe something we're not super familiar with. But this angle right here is kind of nice. It's an acute angle, and we know a lot about acute angles. So the question here is how much further would I need to go to make a full revolution? Okay, and if we can figure out this angle right here, let's call it alpha, then that angle alpha would be a coterminal angle to negative 7 pi over 4. So let's see what we're working with here. Let me scroll down a little bit. All right, so we know we have a full revolution is 2 pi, okay? We already used 7 pi over 4 of a full revolution, so let's see what's left over. Now, you do need to get comfortable with fractions, and I know that can be terrifying for some of you because fractions are they can be a little bit intimidating, but basically we need an LCD here. The LCD would be 4. What would I multiply 1 by to get 4? Well, I would have to multiply it by 4. So I multiply top and bottom by 4. So that tells me one full revolution is really 8 pi over 4. We want to subtract 7 pi over 4, which leaves me with pi over 4. So if I went pi over 4 further, I would have made a full revolution. So that tells me right here that theta, or not theta, alpha is pi over 4. Okay, so let's think about what that means. Secant of negative 7 pi over 4 is the same thing as secant of pi over 4. They are coterminal. They share a terminal side. That means all 6 trig functions are going to be the same, okay? And pi over 4, in case you don't remember, is 45 degrees. And remember, in section 7.3, we looked at 45, 45, 90 triangles, and we looked at 30, 60, 90 triangles. And I said, hey, we've got this table with all the 30, 60, or the 30 degree, 60 degree, and 45 degree trig functions, okay? So if you go back to that, let's think about what secant is. We know that secant is really 1 over cosine of pi over 4. Well, cosine of pi over 4 is root 2 over 2. So that tells me I'm going to get 1 over root 2 over 2, which is really just 2 over root 2. I need to rationalize this, so I want to multiply top and bottom by the square root of 2. So I get 2 root 2 over 2, or just root 2. Okay, so if you have a wacky angle, if you can find a coterminal angle that's a nice, pretty acute angle, it can help you simplify a lot of these and evaluate these trig functions. So let's go up here and go ahead and say, hey, secant of negative 7 pi over 4 is really square root of 2, because we know that secant of negative 7 pi over 4 is equal to secant of pi over 4, and secant of pi over 4 is the square root of 2. Okay, now I'll tell you this right off. Dealing with radians is always going to be harder than dealing with degrees. Degrees, they just kind of make sense. We don't have to deal with the fractions. So this last example is going to be the easiest one. Okay, so 270. I know right off the bat, thinking of 270, it's like if I divided it by 3, I would get 90 degrees. This is also negative, so let's see what this is going to look like. So I've got my vertex at the origin, my initial side on the positive x-axis. I need to go 90 degrees, 90 more, which is 180, and then 90 more than that is negative 270. So theta is negative 270 degrees. Well, negative 270 degrees, that's not something we've forced ourselves to memorize, okay? But if I look at it like this angle right here, let's call it alpha, this would be whatever's left over. So we didn't quite do a full revolution. We did 270 degrees, but not quite all the way to 360 or negative 360. So let's see how many degrees are left over. Now, hopefully this one is easy to see. But you could take 360, subtract 270, and that leaves 90 degrees. So that tells me alpha is 90 degrees. And 90 degrees is just a little bit easier for us to work with. So 90 degrees and negative 270 degrees are coterminal. They share a terminal side. So the trig functions are going to be exactly the same. So if we scroll up here, we have this table where we already found all of the trig functions for those quadrant angles. 90 degrees is a quadrant angle. So let's figure out cosecant of 90 degrees. So cosecant is right here of 90 degrees is 1. So if we go back down to this problem, we know that cosecant of negative 270 degrees is equal to cosecant of 90 degrees. And we know that cosecant of 90 degrees is 1. So that tells me cosecant of negative 270 is also 1. Okay, so there is some power and some magic between these coterminal angles. Again, if you get kind of a wacky angle, see if you can figure out what a coterminal angle is that might be a nice, easier acute angle that we may already remember. So if we can come up with a coterminal angle that's like 30, 60, or 45 degrees, or one of the quadrant angles, that's always going to be really, really helpful. Okay, so that is coterminal angles. Make sure you understand kind of what they are and how they work. Okay.